Hello friends, welcome to this lecture. Myself Amlan. Today I will discuss about Zeeman effect. Zeeman effect was discovered by P. Zeeman in 1896. What is Zeeman effect? When a magnetic field is applied to a substance emitting line spectrum, each spectral line is splitted into several component lines. Though a spectral line before application of the magnetic field was of unpolarized light, the split component lines on application of the magnetic field are polarized. This effect is called Zeeman effect. Okay. There are two types of Zeeman effect. First is normal Zeeman effect and other is anomalous Zeeman effect. Okay. Now what is normal Zeeman effect? When a spectral line is splitted into three components in a magnetic field, when viewed in a direction perpendicular to the magnetic field, is known as normal Zeeman effect. Normal Zeeman effect is obtained from sources of elements like calcium, copper, zinc, cadmium, etc. Okay. So this is normal Zeeman effect. Now, what is anomalous Zeeman effect? When a single spectral line is splitted into four or more lines when observed in a direction perpendicular to the magnetic field is known as anomalous Zeeman effect. Anomalous Zeeman effect is obtained from elements like sodium, chromium, etc. Okay. Now, this effect is not really anomalous as it can be explained by the vector atom model, which is based on the concepts of electron spin and space quantization. This effect is anomalous with respect to Lorentz electronic theory and pre-vector atom model old quantum theory. Anomalous Zeeman effect is more commonly observed than normal Zeeman effect. Okay. Now let's go to the theory of Zeeman effect. That is how we can explain Zeeman effect. Okay. Zeeman effect, both anomalous and normal, can be explained by the vector atom model. Okay. Let us consider an atom of the substance that emits line spectrum. Let the atom contains several electrons and have relatively small nuclear charge, so that the total angular momentum of the atom is produced by Russell-Saunders coupling or LS coupling. Okay. Now let L vector be the total orbital angular momentum of all the electrons of the atom. Let S be the total spin angular momentum of all the electrons of the atom, and J vector denotes the total angular momentum of the atom. Then all being expressed in the unit of h cut are related as L vector plus S vector equals to J vector. Okay. And their magnitudes are given by modulus of L vector equals to root over L into L plus 1, modulus of S vector equals to root over S into S plus 1, and modulus of J vector equals to root over J into J plus 1. Okay. All being expressed in the unit of h cut. Okay. Now here L is the total orbital quantum number of the atom. S denotes the total spin quantum number of the atom, and J is the total angular momentum quantum number of the atom. Okay. Now the magnetic dipole moment mu L, due to the spin motion, due to the orbital motion of all the electrons of the atom, is given by mu L equals to minus EH by 4 pi ME into L vector. Okay, and the magnetic dipole moment mu s vector due to the spin motion of all the electrons of the atom is given by mu s vector equals to minus 2 EH by 4 pi ME into S vector. Okay. Now here E is the electronic charge, H is Planck's constant, and Me is the mass of electron. Okay. Now dividing these two equations, we get modulus of mu s by modulus of s equals to 2 into modulus of mu l by modulus of L. Okay. Now we draw mu l vector and mu s vector. Okay. Suppose this is L vector. Okay. First we draw L vector and S vector. This is L vector and suppose this is S vector. And the resultant of L vector and S vector is J vector. So this is J vector. Okay. Now we draw mu l vector and mu s vector. Okay. Now mu l vector has same magnitude but opposite direction as that of L vector. Okay. So this is mu l vector. Now mu s vector has magnitude twice as that of S vector and in a direction opposite to the S vector. So this is mu s vector. Okay. Now the resultant of mu l vector and mu s vector is mu vector, and so this is mu vector. Okay. This is mu vector, that is resultant of mu l vector and mu s vector, and this is the direction of J vector. Okay. So this is the direction of mu vector and this is the direction of J vector. Okay. Now we see that the resultant magnetic moment mu has a direction different from that of J vector. Okay. Now due to the spin orbit coupling, vector L and S precede about the direction of J with equal frequency, each maintaining a constant angle with J. So the vector mu L and mu S also precedes about the direction of J with the same frequency as that of L and S. The vectors mu L and mu S add vectorically to give the resultant magnetic moment mu of the atom. Okay. Now as mu L and mu S precedes about the direction of J, mu also precedes about the direction of J. Okay. Now during the precision of mu about the direction of J, its component mu J in the direction of J remains constant and its component mu perpendicular in a direction perpendicular to J, which rapidly rotates about the direction of J, vanishes on time average. So mu J is the effective magnetic moment of the atom. Obviously mu J will be the sum of resolved part of mu L and mu S in the direction of J. Okay. Now let's calculate mu J. Okay. Now let's calculate mu J. Now mu J equals to mu L cos of angle L comma J plus mu S cos of angle S comma J. Okay. Now if we put the value of mu L, then we will get this is equals to mod of EH by 4 pi ME into L modulus into the value of cos of angle L comma J is modulus of j square plus L square minus S square by 2 into modulus of j into modulus of L. Okay. Plus, if we put the value of mu s, then we will get 2 into EH by 4 pi ME into S modulus, and the value of cos of angle S comma J is modulus of J square plus modulus of S square minus modulus of L square by 2 into modulus of J modulus of S. Okay. Now here modulus of L will be cancelled, and here modulus of S will be cancelled. Now here both numerator and denominator we multiply modulus of j, and here also both numerator and denominator we multiply modulus of j. Okay, and if we simplify this equation, we will get this is equals to EH by 4 pi ME into modulus of j, and this is equals to 2 modulus of j square plus modulus of L square minus modulus of S square plus 2 into j square plus 2 S square minus 2 L square. Okay. Now this can be written as EH by 4 pi ME into modulus of j, and this is equals to 2j square plus j square plus S square minus L square by 2 into modulus of j square. Okay, and this can be written as EH by 4 pi ME into modulus of j into 1 plus j square plus S square minus L square by 2 into j square. Okay. Now if we put the value of modulus of j, modulus of L and modulus of S, then we will get this is equals to EH by 4 pi ME into root over j into j plus 1. Okay, to 1 plus j into j plus 1 plus S into S plus 1 minus L into L plus 1 by 2 into j into j plus 1. Okay, so this is mu j. So this is equals to, now let this term is equals to mu of b. So this is mu b into root over j into j plus 1, and suppose this is equals to g. So this is g. So mu j equals to g into root over j into j plus 1 into mu b. Okay, where mu b equals to EH by 4 pi ME. Okay, mu b is called Bohr magneton. Okay, and G equals to 1 plus j into j plus 1 plus S into S plus 1 minus L into L plus 1 by 2 j into j plus 1. Okay, G is called Landesi factor or splitting factor. Okay, now suppose magnetic field acts in this direction. Okay, so this is B vector, and suppose J vector is in this direction. So mu J will be in this direction. So this is mu J vector. And suppose the angle between J vector and B vector is theta. Okay. Now when a magnetic field B of relatively low value is applied to the atom, the spin orbit coupling persists, and L and S combine to produce J, and J takes up discrete orientation, being inclined at such angle theta with B that the component of J in the direction of B is quantized as modulus of J cos theta equals to mj. Okay, or cos theta equals to mj by modulus of J equals to mj by root over j into j plus 1. Okay, where mj is the total magnetic moment of the atom. Okay, now due to the interaction between mu j and B, atom has additional energy, and due to the interaction between mu j and B, j will precede about the direction of B. Okay, and due to the interaction between mu j and B, the atom has additional energy given by delta E equals to minus mu j dot B. Okay, so this is equals to minus mu j B cos of angle. Now the angle between mu j and B is 180 minus theta. So this is 180 degree minus theta, that is mu j B cos theta. Okay, now here mj is the total magnetic quantum number of the atom that can take 2j plus 1 number of values from plus j to minus j in equal steps of unity. Okay, now here if we put the value of mu j, then we will get g into root over j into j plus 1 into eh by 4 pi me into b, and the value of cos theta is mj by root over j into j plus 1. So this is mj by root over j into j plus 1. Now this term will be cancelled, and at last we get g mj into ebh by 4 pi me. Okay, so this is delta E. Okay, so E is equals to E0 plus delta E, where E is the energy of the atom in presence of magnetic field. Okay, so energy of the atom in the magnetic field is E equals to E0 plus delta E. Now we put the value of delta E. This is equals to E0 plus GMJ into EBH by 4 pi ME. So this is the energy of the atom in the magnetic field. Now here E0 is the energy of the atom in absence of magnetic field. Okay, now since mj can have 2j plus 1 number of values, the magnetic field splits the energy level E0 into 2j plus 1 number of closely spaced sublevels. Okay, now when an atom in the magnetic field suffers a transition from state 1 of higher energy E1 to state 2 of lower energy E2, a photon of frequency nu will be emitted, and nu equals to E1 minus E2 by h equals to now if we put the value of E1 and E2, then we will get E10 plus G1 MJ1 into EBH by 4 pi ME. Okay, so this is the value of E1 minus E20 plus G2 MJ2 into EBH by 4 pi ME by H. Okay, so this is equals to E10 minus E20 by H plus G1 MJ1 minus G2 MJ2 into EB by 4 pi ME. Okay, so this is nu. Now here E10 is the energy of the atom in the state 1 in absence of magnetic field, and E20 is the energy of the atom in the state 2 in absence of magnetic field. Now in absence of magnetic field, the transition of an atom from state 1 to state 2 causes the emission of a photon of frequency nu 0 equals to E10 minus E20 by h. Okay, so we may write nu equals to nu 0 plus G1 mj1 minus G2 mj2 into, suppose this is equals to delta nu. So this is delta nu, where delta nu equals to EB by 4 pi me. Okay. So this is nu. Now here selection rule is delta mj equals to 0 plus minus 1. The transition which satisfies this following selection rule can actually occur. Okay. Now, in case the atom has even number of optical electrons, okay, in case the atom has even number of optical electrons, its states with s equal to 0 are possible, and in such case j equals to L. And so in this case, if we calculate the value of Landé-G factor, then we will get G equals to 1. Okay. And so from this equation we may write nu equals to nu 0 plus mj1 minus mj2 into delta nu. Okay. Now when mj1 minus mj2 equals to 0, nu equals to nu 0. When mj1 minus mj2 equals to minus 1, nu equals to nu 0 minus delta nu. When mj1 minus mj2 equals to plus 1, nu equals to nu 0 plus delta nu. Okay. So this gives the frequencies of the split components of a spectral line in normal Zeeman effect. Okay. Now vector atom model cannot explain the polarization of the split component lines. Quantum electrodynamics said that in transverse view, a line corresponding to mj1 minus mj2 equals to 0 is linearly polarized with electric vector parallel to the applied magnetic field and are called pi components, and the line corresponding to mj1 minus mj2 equals to plus minus 1 are linearly polarized with electric vector perpendicular to the applied magnetic field and are called sigma components. Okay. Now, in case the atom has odd number of optical electrons, S is an odd multiple of half, and so S equal to 0 is not possible, and so G does not equals to 1, and as a result the number of split component lines will be greater than that in the normal Zeeman effect, and so the effect is anomalous Zeeman effect. Now for example, magnesium 12 and calcium 20 atom have two optical electrons. So we have S equals to 0 and S equals to 1. Now for in the case S equals to 0, Z equals to 1. And so the spectral line due to the transition of these atoms between two states with S equal to 0, that is singlet state, will cause normal Zeeman effect. Now the number of optical electrons for sodium 11 atom is 1. So for sodium 11 atom, S equals to half, and so G does not equals to 1, and so the sodium 11 spectrum shows anomalous Zeeman effect. Now an aluminium 13 atom contains 3 optical electrons. So for aluminium 13 atom, S does not equals to 0. So aluminium 13 atoms also shows anomalous Zeeman effect. Thus, we can explain both normal and anomalous Zeeman effect by vector atom model. Okay, thank you for watching this video.